So a tetrahedron is like a three-sided pyramid of sorts. Okay? So you got one triangle here, one triangle here, one triangle on the back, one on the bottom. So four triangles, a triangle on each side, four sides, and four corners. 1, 2, 3, 4 corners, okay? That's a tetrahedron. A tetrahedral is like I put something in the dead center of this, in the middle of that little pyramid, and I draw lines to each of those corners. So here's our center right in the middle of that. I'm drawing a line up to the peak, and down here to this corner, and down here to this corner, and down here to this corner. Okay, that's a tetrahedral. Now, the problem is, if you look at that, you can't tell that's three-dimensional. I can kind of tell that's three-dimensional, but you can't tell this one's three-dimensional. So to make it clearer that it's three-dimensional, I need some kind of a perspective. So that dotted line in the back gives me some perspective. For perspective on something like this, what we usually do is we make a triangle, dark triangle like that, that signals to the person who's looking at this that that's swinging out toward us away from the paper. And we make this line that's going back here behind, it's going to that back corner back there, this line back here, we make it a dotted line. And that shows it's kind of behind everything, like our dotted line along the base of this pyramid sort of shape, this tetrahedron. So let me make it a dotted line then. All right? Does that make sense? So that's a tetrahedron as far as the shape. Now, if we're trying to figure out the shape of molecules, then we've got to go through some more stuff to figure out how do we get there. Let's see. Let's take and put together nitrogen with 3 hydrogens. So write the electron dot notation for hydrogen and do the sharing arrangement. If you were reviewing your notes from units 1, 2, and 3, this is a big part of it. We went and did a lot of this stuff. Okay? If you're just waiting for me to show you, that's passive learning. You're not really learning if you're passively learning. You're not learning very much. Not learning enough.
What if you didn't know how to do it and you didn't want to,
Well, but you still should have an idea of what it looks like. Even if you didn't know how to do it, you could look at your notes and see, well, it's got dots and circles around it. Yeah? Huh? Okay, all right. Then from the sharing arrangement, we're going to get the Lewis dot formula, where we squeeze the electrons in between. All right, and that's all we really need to start figuring out molecular shapes. Now, to figure out molecular shapes, you're going to count the sets of electrons around the central atom. Now, sets can be pairs, can be a set of 4, can be a set of 6. Actually, we can have sets of odd numbers too. Those are so rare. We don't deal with them in high school chemistry very much. But there's how many sets of electrons around this central atom? 4 of them. 4 sets of electrons around a central atom will give you a tetrahedral. Okay? 4 sets of electrons around a central atom will give you a tetrahedral. Tetrahedrals are 3-dimensional arrangements that have angles of 109.5 degrees. So here's our nitrogen, which is either the atom of interest, or in this case it's the central atom too. Not always is the atom of interest the central atom, because we could have a really long molecule. We have to look at each of the bonds all the way through the whole thing to figure out shapes. And this is the sort of the beginning of figuring out all that if you're going to go into medicine or something. I mean, why is it that proteins have the shapes they have? This is the beginning of understanding that. Okay? So, or for that matter, why do medicines have the shapes they have? They have to have a certain shape sometimes to do their job. Yeah, like pills. Really. I mean, your hemoglobin in your blood, the exchanges oxygen and CO2 in your lungs. If it weren't for its shape, it wouldn't do its job. It's not just some chemical process. It's actually a shape thing. Okay? It's like a big container, and there's a CO2 or an oxygen trapped in the middle. And the pH of your blood changes the shape to let the CO2 out and let the oxygen in. That's the way it works. Okay? It's like opens up and closes. Okay? And it's sort of a clamshell kind of thing. Not really a clamshell thing. All right. So a tetrahedral means I have 4 arms, and they're all 109.5 degrees apart. Now, I can't get 109.5 degrees if I'm just on this flat surface. I've got to have two of them on a flat surface, but one of these has to come out toward you, and one has to go back behind this piece of paper. And so we have to use a kind of modified or simplified perspective drawing to show that. To show the one that's coming out toward you, we use this triangle. Okay? Or you could darken it in and make it a dark, black triangle. Okay? And then to go back behind the paper, we usually use a dotted line. That's what we're showing. I have no idea what they're watching. Let's just focus here. Okay. Now I've got 4 sets of electrons around the central atom. I want to put those 4 sets of electrons on each of these sort of arms to show the direction of this, where these electrons are located. Okay? Then from this one, I'm going to replace 3 of these sets with the atoms they're shared with, because I'm only sharing 3 atoms. I've got one lone pair up here. This next drawing is going to leave the lone pair alone. So I'm going to leave my lone pair up here. It doesn't really matter which one you leave your lone pair on. There are some shapes that we don't get to in this class where it does matter. It just doesn't matter with a tetrahedral. Okay? And I'm going to put a hydrogen out here on this arm and share those electrons in that bond. I want to put a hydrogen out here on this one that's swinging out toward you, and put a hydrogen on one that's swinging back behind. Okay? And that, we call this just the electron pair shape, and it's a tetrahedral. And we call this a modified electron pair shape, and it's also a tetrahedral. So it's kind of like first and last names. Modified electron pair shape, first name, tetrahedral, last name. Or vice versa, it doesn't really matter. It's like when we write your names on your papers, you use your last name first. Doesn't really matter, okay? It matters to me, but it doesn't really matter in the long run. Still your name. All right, and this is a tetrahedral, but it's a modified electron pair shape because we've got electron pairs here, but we modified it by putting the atoms on there that belong there. Then to get to the actual molecular shape, we remove the electron pair. Okay? So then we have this. He wanted to know the difference between trigonal planar and trigonal pyramidal. And this is trigonal pyramidal. Okay? It's like a 3-sided pyramid. Okay? And that's why we call it trigonal pyramidal. Now trigonal planar, on the other hand, is going to be doesn't have a peak here, it's flat. So let's look at maybe this stuff here. Okay? All right, let's take our atom of interest, the carbon, which also in this case happens to be the central atom. And we're going to arrange the pairs of electrons 3-dimensionally around that central atom. Well, there's 3 sets now, okay? This set of 4, all the electrons share between 2 nuclei or any lone pairs. Those make up sets. So I've got 1 set, 2 sets, and 3 sets. Okay? 3 sets of electrons. So I need 3 arms. Well, those are the furthest we can get those from each other. Remember, the whole idea here is to get these electrons pairs as far apart as we can get them. We go back to the whole idea we talked about earlier, where we said that we can put 2 electrons in the same space because they have opposite spins. It's called quantum entanglement. And then after we get those 2 together, we can't get other electrons in the same space because their like charges repel. They're all negative. They're going to repel each other. So by putting these on these arms here like this, they're as far apart in space as I can get them and still have them attached electromagnetically to this carbon nucleus. All right? Well, that's flat. And if I do the next step in the process then, I'm going to put hydrogens here and here on the pairs of electrons. The pairs of electrons are here and here. And put the oxygen over here on the arm where I have 4 electrons. Okay? And that's trigonal planar. So this is trigonal pyramidal. And you can say that's its first name, and its last name is that it's a molecular shape. Okay? And so we can call this first name trigonal planar. Okay? And its last name is molecular shape. We don't have too many people in here that have double first names. Okay? But we do have some people who have double last names. Okay?
Where? Anybody who have a double last name?
I wish it might.
I don't want to call it. Huh? It's pretty common in Latin countries.
Sure, sure.
I wish it might first name and my
Yes.
Just to kind of, this is going all the way back to the
Is it about this stuff? Okay. Yep. Okay.
So, this is like going all the way back. But, the C in the middle would that be SP2?
Ah, very good, yes. Because there's a double bond here. Okay, we've got one sigma bond and one pi bond. So we add up all the sigma bonds. That's 1, 2, 3. There are no lone pairs. So 3 is the sum of all the lone pairs and sigma bonds. That's an sp2 hybridization.
Wait, okay.
Oh, I'm sorry. Did I confuse you?
Well, no.
Okay. Double bonds have a sigma bond and a pi bond. This is the sigma bond here. Okay? Now this is with carbon and carbon, but in our illustration on this, what we're doing just now, it's between carbon and oxygen. Okay? Double bonds have a sigma bond. Okay? We have a sigma bond going this way, a sigma bond going here, and a sigma bond going here. Or, if in 3 dimensions, there's a sigma and a pi bond going this way, a sigma bond going this way, and a sigma bond going this way. Okay? If we add up the sum of all the sigma bonds and lone pairs, and it equals 3, that's an sp2. That's one way to think about it. Okay? It's a good sort of self-check mechanism. Okay? I know some people in college organic chemistry use that a lot to almost exclusively instead of actually understanding the underlying structure of where we get it from. And they manage to survive and do pretty good in organic chemistry. But it's probably better if you really understand the actual structures underneath. Yes? Yeah. All right, that's all the questions about this?